125 light Webb's-Arch. In 2023, astronomers found a runaway black hole that had been ejected from its galaxy, and behind it, a trail of newly formed stars stretching 200,000 light-years, created by the shock of its passage through intergalactic gas. Subscribe, there's a new one every few days. This is White Space, settle in. There are objects in the universe so extreme that the laws of physics as we experience them begin to feel like suggestions. Among the most extreme of all is the black hole, a region of space where gravity has won every argument it has ever made. No light escapes, no signal reaches us. And yet, for something so famously invisible, black holes turn out to be extraordinarily active, varied, and in their own way almost theatrical. The concept of a region from which light cannot escape has existed in theoretical physics for over 2 centuries. In the late 18th century, the English geologist John Michell proposed that a sufficiently massive and compact body would have an escape velocity exceeding the speed of light, and therefore would be invisible to any outside observer. He called such objects dark stars. The idea was elegant and entirely in keeping with Newtonian mechanics, but it lay dormant for over a century, awaiting a theory capable of treating gravity and light within a single framework. That theory arrived with Einstein's general theory of relativity in 1950. In Einstein's picture, gravity is not a force transmitted between masses, but the curvature of space-time itself, and light, having no mass, is nonetheless deflected by this curvature, because it follows the shortest possible path through curved geometry. A sufficiently deep curvature creates a region from which no path leads outward. In 1916, the German physicist Karl Schwarzschild, working from the trenches of the First World War, derived the first exact solution to Einstein's field equations, a solution describing spacetime around a perfectly spherical, non-rotating mass, the critical radius within which nothing could escape. What we now call the Schwarzschild radius emerged directly from his equations. For an object with the mass of the Earth, that radius is about 9 millimeters. For the Sun, it is roughly 3 kilometers. The concept was mathematically rigorous long before there was any observational evidence that such objects actually formed in nature. General relativity also predicted something troubling about black holes. Once anything crossed the event horizon, it was gone forever. Information about the infalling object, its composition, its quantum state, appear to be irretrievably lost. This troubled physicists deeply because quantum mechanics insists that information is never truly destroyed. It may become scrambled, but it must in principle remain recoverable. The conflict between these two foundational theories of physics crystallized in 1974, when Stephen Hawking demonstrated that black holes are not entirely black. Applying quantum field theory to the curved spacetime near a black hole's event horizon, Hawking showed that particle-antiparticle pairs produced by quantum fluctuations near the horizon can be separated. One particle falls inward, the other escapes. The escaping particles, now called Hawking radiation, carry energy away from the black hole, causing it to slowly lose mass and, over immense timescales, evaporate entirely. But the radiation is thermal, it carries no information about what fell in. If Hawking's calculation is exactly correct, the information is truly lost, violating a principle that quantum mechanics treats as inviolable. This is the black hole information paradox, and it remains one of the deepest unresolved problems at the interface of general relativity and quantum theory. Recent work, including contributions from Juan Maldacena and Geoffrey Pennington, has suggested that information may escape encoded in subtle correlations in the Hawking radiation. But the mechanism remains the subject of intense ongoing debate. The evidence that black holes physically form in nature came slowly. By the 1960s and 1970s, X-ray observatories carried aboard early satellites began detecting intense radiation from compact regions in binary star systems, Sources like Cygnus X1, where a stellar mass companion appeared to be spiraling into an invisible object far too compact and massive to be a neutron star. The inference was difficult to avoid. These were black holes, not theoretical constructs, but physical objects actively feeding, radiating, and interacting with their environments. The theoretical framework for understanding them deepened rapidly through the work of Roger Penrose, who proved in 1965 that singularities, regions of infinite density, are an inevitable consequence of gravitational collapse under very general conditions. Penrose's singularity theorem, together with Hawking's analogous result applied to cosmology, established that singularities are not mathematical artifacts, but genuine features of space-time predicted by classical general relativity. What physics does inside a singularity, where density becomes infinite and the known equations break down, remains unknown and is expected to remain so until a complete quantum theory of gravity is developed. The no-hair theorem, established through the work of Werner Israel, Brandon Carter, and others in the late 1960s and early 1970s, proved that a black hole in equilibrium is completely characterized by just three quantities: its mass, its spin, and its electric charge. Everything else, the composition of the infalling matter, its temperature, its chemical structure, is erased from the external universe the moment it crosses the horizon. The black hole does not care what it swallowed. Two black holes with identical mass, spin, and charge are, in every externally measurable sense, identical objects. This radical simplicity is itself a profound statement about the nature of gravity and information. The reason we know black holes exist at all comes down to the universe's willingness to give indirect clues. One of the most striking is a phenomenon called gravitational lensing. When a black hole sits between Earth and a distant source of light, the immense curvature of space-time bends those light rays around it like a lens made not from glass but from pure geometry. The more massive the lensing object, the more dramatic the distortion. Rings, arcs, and multiple ghost images of the same background galaxy appear in the sky. In the most geometrically perfect cases, a complete ring of light, called an Einstein ring, forms around the lensing mass, with the background source magnified and distorted into a continuous halo. This technique has become one of astronomy's most important tools, letting us map mass that would otherwise remain completely hidden. Dark matter, whose presence we infer almost entirely from its gravitational effects, is routinely traced using lensing maps. Isolated black holes wandering through the galaxy's disk can be detected through the brief brightening they cause in background stars. As they pass across the line of sight, a technique called microlensing that has now confirmed the existence of multiple isolated stellar mass black holes in our galaxy. But gravitational lensing is only the beginning. Over the past several decades, observations have revealed that black holes are not simply inert bits in the cosmic landscape. They spin, they feed, they collide, they wander, they steal, and they grow into structures so massive that our current theories still struggle to explain how they got there so fast. Here are 10 of the most remarkable behaviors that black holes have been confirmed or strongly suspected to exhibit. The first is rotation, and not gentle rotation. Black holes spin at rates that challenge intuition. The black hole at the center of M87, the giant elliptical galaxy located about 55 million light-years away, has been directly imaged by the Event Horizon Telescope, a planet-spanning network of synchronized radio observatories that achieves angular resolution equivalent to reading a newspaper on the Moon from Earth. The image revealed a glowing ring of hot plasma surrounding a central shadow, the photon ring, where light orbits so close to the black hole that it curves back on itself, and the shadow, which marks the region inside which no light can escape. M87's black hole spins at a significant fraction of the theoretical maximum permitted by general relativity. As it spins, it drags space-time itself around with it in a process called frame dragging, a phenomenon predicted by Einstein and later formalized by Joseph Lenz and Hans Stiring in 1918, then confirmed observationally by the Gravity Probe B satellite in Earth orbit in 2011. Matter falling towards such a black hole doesn't simply drop in a straight line. It spirals inward through a superheated accretion disk, with temperatures in the innermost regions reaching billions of degrees, radiating across the electromagnetic spectrum in a display that can outshine entire galaxies. The Kerr metric, the generalization of the Schwarzschild solution to rotating black holes, derived by Roy Kerr in 1963, predicts that a maximally spinning black hole develops an ergosphere, a region outside the event horizon where space-time itself rotates faster than light, and from which energy can in principle be extracted through a mechanism called the Penrose process. In this process, an object entering the ergosphere and splitting into two fragments can arrange for one fragment to fall inward on a retrograde orbit carrying negative energy as measured from outside, while the other fragment escapes carrying more energy than the original object brought in. The rotational energy of the black hole is thereby tapped over astronomical timescales, this process operating through magnetic fields in the accreting plasma rather than through classical objects is thought to be responsible for launching the relativistic jets seen in active galactic nuclei. Second, black holes have a pronounced tendency to merge. The binary black hole system OJ287, located roughly 3.5 billion light-years from Earth, is one of the most studied examples. It consists of a supermassive black hole orbiting an even larger one, with the primary weighing approximately 18 billion solar masses, making it one of the most massive black holes known, and a smaller object periodically punching through the accretion disk of the larger, producing characteristic flares that have been tracked for over a century using archival photographic plates. The timing of these flares has been used to test predictions of general relativity with extraordinary precision, because the orbital dynamics of such a system are sensitive to the space-time curvature the smaller black hole experiences as it moves. Such binary systems are not just curiosities, they represent an intermediate stage in the hierarchical assembly of the most massive objects in the universe. Supermassive black holes weighing billions of solar masses almost certainly did not form from single collapsing stars. Instead, they accumulated through sequences of mergers, smaller black holes coming together in dense stellar environments, then growing further by cannibalizing surrounding gas. The final parsec problem, the theoretical difficulty in getting two supermassive black holes close enough to actually merge, since gravitational wave emission only becomes efficient at very small separations, remains an active area of research, with potential solutions involving interactions with surrounding stars or gas clouds that carry away angular momentum. The laser interferometer pulsar array experiments, networks of millisecond pulsars whose timing is affected by the gravitational waves passing between them and Earth, have recently reported evidence for a stochastic gravitational wave background consistent with a cosmic population of inspiraling supermassive black hole binaries. If confirmed, this would represent the detection of gravitational waves from a source population distributed throughout the observable universe, an entirely new window on the dynamics of galactic nuclei across cosmic time. Third, black holes throw things. When a star wanders too close to a black hole, tidal forces tear it apart, a tidal disruption event. The stellar material stretches into a long stream, some falls into the black hole, while the rest is flung outward at extraordinary velocities. The event, a SAS and 14Li, detected in 2014 in a galaxy about 290 million light-years away, showed a star being consumed and its debris ejected in a structured outflow. Packets of material with masses comparable to small planets were being launched into the surrounding interstellar medium at millions of kilometers per hour. Theorists estimate that a single tidal disruption event can release roughly the equivalent energy of 100 million supernovae concentrated into a compact region over a period of months. Perhaps even more dramatic are the relativistic jets that some tidal disruption events produce, narrow beams of plasma accelerated to very nearly the speed of light and pointed directly at Earth. The event AT2019 DSG showed a delayed jet launch emerging roughly 150 days after the initial disruption, suggesting that jet formation requires time for the infalling debris to establish a coherent accretion geometry before the magnetic fields are organized enough to drive a directed outflow. Tidal disruption events are now being detected at a rate of several dozen per year by wide-field optical surveys, providing a statistical sample of how black holes of different masses feed on stars of different types, a new empirical probe of black hole demographics across the universe. Fourth, black holes preserve evidence of their host galaxy's history. The dusty torus, the dense ring of gas and dust orbiting a black hole at a distance of several light-years, functions as something like a geological record. In NGC DES 68, located about 47 million light-years away and studied in detail by the ALMA radio telescope array, the torus displays asymmetries and structural details that suggest the galaxy experienced a major gravitational interaction, possibly a merger, at some point in its past. The torus is not simply a feeding reservoir. It is a document beyond the torus. The broader galactic environment also carries a record. The stellar kinematics of the bulge, the chemical abundances of different stellar populations, the distribution of globular clusters and their ages. Active galactic nuclei also leave physical marks on their surroundings, heating and expelling the gas that would otherwise feed star formation, or compressing gas clouds and triggering bursts of new star formation, depending on the geometry and energy of the interaction. This feedback mechanism, the coupling between a central black hole and its host galaxy, is now understood to be one of the primary regulators of how quickly galaxies grow and how their star formation histories evolve over cosmic time. Fifth, black holes can consume matter at rates that strain comprehension. The quasar ULAS J1120 plus 0641, one of the most distant quasars known and observed as it appeared just 770 million years after the Big Bang, hosts a black hole containing about 2 billion solar masses. It is feeding at rates approaching the theoretical Eddington limit, the point where radiation pressure from infalling material should, in principle, hold further accretion. That such a massive object existed so early in cosmic history is one of the outstanding unsolved problems in astrophysics. Scenarios involving super Eddington accretion, where the infalling material is so dense that radiation becomes trapped and advected inward rather than escaping, have been proposed to explain how early black holes could grow so rapidly. Either way, ULAS J1120 plus 0641 feeds with a hunger that makes the word voracious feel inadequate. The broader population of high redshift quasars has revealed that the most massive black holes in the universe were, paradoxically, the first to stop growing. This phenomenon, called downsizing, runs counter to the naive expectation that larger things take longer to assemble. The most massive black holes reached their final masses within the first few billion years of cosmic history, while smaller black holes in lower mass galaxies continue growing today. The physical mechanism responsible for this reversal of assembly order remains an active area of theoretical investigation. Sixth, black holes leave. When two supermassive black holes unite, the gravitational waves emitted during the final coalescence are not always symmetric. An asymmetric burst can deliver a powerful recoil kick to the resulting merged black hole enough, in some cases, to eject it entirely from its host galaxy. Candidate examples of this phenomenon have been identified using the Hubble Space Telescope, where a luminous compact object appears offset from the center of its parent galaxy and moving away from it at millions of kilometers per hour. A black hole with the mass of a billion suns wandering the intergalactic void, untethered, invisible, but still distorting everything around it. In 2023, a particularly dramatic candidate was identified, a trail of newly formed stars stretching 200,000 light-years, apparently generated by the compression of intergalactic gas as a runaway black hole plowed through it. The wake of the object was brighter than the galaxy it had left behind. Whatever created it had departed at a significant fraction of the speed of light. The possibility that intergalactic space contains a population of wandering massive black holes, invisible except through their gravitational lensing of background sources and the rare tidal disruption events they produce, opens a new chapter in black hole census taking that future surveys are beginning to address. 7th, black hole steal mass from larger neighbors. Analysis of gravitational wave detections by LIGO and Virgo revealed that some merging black hole pairs have masses significantly higher than expected from standard stellar evolution. One proposed explanation involves hierarchical growth in dense galactic nuclei. Two stellar mass black holes can gradually draw in gas and material that a nearby supermassive black hole is actively consuming, growing heavier than their origins should permit before eventually spiraling together and merging. This hierarchical merger pathway implies that some of the black holes detected by gravitational wave observatories are themselves the products of earlier mergers, second-generation black holes formed from the coalescence of two first-generation objects. Distinguishing first-generation from second-generation black holes using gravitational wave signatures is an active area of theoretical work, with predictions that second-generation objects should show characteristic spin configurations that first-generation mergers would not. As gravitational wave detectors improve in sensitivity with upgrades to LIGO and Virgo and the eventual deployment of space-based detectors like the Laser Interferometer Space Antenna, the statistical power of the gravitational wave catalog will grow dramatically, enabling population-level studies of black hole growth and assembly across cosmic history. 8. Black holes use magnetic fields as tools. The galaxy Centaurus A, the closest active galactic nucleus to the Milky Way at about 13 million light-years, hosts a black hole surrounded by measurably strong ordered magnetic fields that channel infalling plasma, regulate the structure of the accretion disk, and play a direct role in launching the relativistic jets extending hundreds of thousands of light-years from the galaxy's core. Measurements of the magnetic field threading the accretion disk of M87's black hole, made possible by the Event Horizon Telescope's ability to measure the polarization of radio waves, revealed that the field is organized in loops and spirals consistent with the theorized magnetically arrested disk configuration, a state in which the magnetic pressure is strong enough to periodically halt accretion entirely, producing episodic flares as accumulated material periodically breaks through. The interplay between magnetic fields and accreting plasma is governed by magnetohydrodynamics, a branch of physics that combines Maxwell's equations with the equations of fluid dynamics and remains one of the computationally most demanding problems in astrophysics. Simulations of accretion flows around spinning black holes now require supercomputers running for months to model dynamics occurring over timescales of hours near the event horizon. 9th, black holes hide in places where they should, by all rights, be too large to fit. M60 UCD1, an ultra-compact dwarf galaxy located roughly 50 million light-years away, contains about 140 million stars packed into a radius of just 160 light-years, and at its center sits a black hole of approximately 21 million solar masses, accounting for more than 15% of the galaxy's total mass. One hypothesis holds that M60 UCD1 is the stripped remnant of a once larger galaxy, with most of its outer star tidally removed by the gravitational influence of its neighbor M60 over billions of years, leaving only a dense core with an outsized remnant nucleus. If this interpretation is correct, then ultra-compact dwarf galaxies throughout the universe may be the skeletal remains of galaxies that once rivaled our own in size and complexity, reduced over billions of years of gravitational interaction to dense, glittering fragments with oversized black holes as the only visible marker of what they once were. This stripping process is not confined to extreme cases. A continuous spectrum of galaxy transformation, from gentle tidal effects at large separations to catastrophic stripping at close passage, reshapes dwarf galaxies throughout the universe's dense environments, like galaxy clusters over cosmic timescales. 10th, and perhaps most sobering, black holes can grow fast enough that were one of the most extreme examples placed in our galaxy's center, the resulting radiation would be visible in daylight and lethal to life on Earth. The quasar J2157, discovered in 2018, hosts what is currently the fastest growing known black hole in the observable universe. It adds mass equivalent to roughly the entire Sun every 2 days. Its luminosity is correspondingly spectacular, thousands of times brighter than the entire Milky Way. It formed and grew to this scale in the first 2 billion years of cosmic history, in an era when the universe itself was undergoing rapid and dramatic structural change. If placed at the center of the Milky Way, J2157's radiation output would strip the ozone layer from Earth's atmosphere and sterilize the planetary surface with high-energy X-rays and gamma rays. The calm of our own galactic center, where Sagittarius A sits quietly accreting at well below its Eddington limit, is something of a cosmic gift. These 10 behaviors are not edge cases. They represent the range of what black holes are known to do, and that range is considerably wider than the simple image of a featureless void that once passed for a complete picture. The universe that contains these objects also raises questions at a different scale. How did everything begin? How large is it? What, if anything, does it look like from the outside? These are questions that lie at the intersection of physics, mathematics, and philosophy, and over the past century our answers have changed dramatically enough to suggest they will continue to change. The dominant cosmological model holds that the observable universe originated approximately 13.8 billion years ago in a state of extraordinary density and temperature, a singularity from which space, time, and energy all emerged together. The expansion that followed was not an explosion in space, it was an expansion of space itself, carrying matter outward in all directions simultaneously. In this model, there is no center, there is no edge. Every point in the universe is, in some meaningful sense, the center of its own observable sphere. To speak of the Big Bang as occurring at a particular location is to misunderstand the geometry. The singularity was not a point in space, but a moment in time, and every location in the present universe was, at that moment, compressed into the same singularity. The first fraction of a second after the Big Bang is now described in extraordinary quantitative detail. At 1/10 millionth of a trillionth of a trillionth of a trillionth of a trillionth of a second after the beginning, a time so brief that no unit of human experience provides a useful analogy, the temperature was so high that the 4 fundamental forces were unified into a single interaction. As the universe cooled, symmetry broke, gravity separated first, then the strong nuclear force, then the electroweak force split into electromagnetism and the weak force. Each transition released energy and imprinted structure. By the time the universe was 1 microsecond old, quarks had combined into protons and neutrons. By 3 minutes, nuclear fusion had produced the first atomic nuclei, roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium and deuterium. This primordial nucleosynthesis prediction, matching the observed cosmic abundances of light elements to high precision, is one of the most powerful confirmations of the Big Bang model.
But the Big Bang model is not without gaps. The flatness problem is particularly acute. For the universe to have the spatial geometry we observe today, very close to flat, the energy density in the earliest moments must have been tuned to the critical value with extraordinary precision. The horizon problem is equally puzzling. Regions of the universe separated by distances greater than light could have crossed since the Big Bang have nearly identical temperatures in the cosmic microwave background. The answer, proposed by Alan Guth in 1980 and developed further by Andrei Linde and others, is cosmic inflation, a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second, during which the observable universe expanded by a factor of at least 10 to the 26th power. This expansion would have stretched any initial curvature flat, brought all parts of the observable universe into causal contact before inflation began, and generated the primordial density fluctuations that seeded all subsequent structure through the quantum fluctuations of the inflaton field. Into the remaining gaps, alternative and supplementary theories have been proposed. The steady-state model proposed that matter is continuously created to maintain a constant average density as expansion proceeds, a model ruled out by the discovery of the CMB. The cyclic cosmology of Steinhardt and Turok proposes that the Big Bang was not a unique event, but one in a sequence with the universe undergoing repeated cycles of expansion and contraction. The ekpyrotic model suggests our universe was formed when two higher dimensional branes collided with the Big Bang, representing the energetic result of that impact, a model making specific predictions about the pattern of primordial gravitational waves that differ from standard inflationary cosmology. Loop quantum cosmology, which applies the techniques of loop quantum gravity to the early universe, replaces the Big Bang singularity with a big bounce, a transition from a previous contracting phase to the current expanding one, with a quantum geometry of space-time preventing the density from diverging to infinity. And then there is the possibility that our universe is itself one of an enormous or infinite number of universes, a multiverse. Inflationary cosmology naturally produces a picture in which inflation continues indefinitely in some regions while ending in others, with each terminated region constituting a separate universe with potentially different physical constants. In this picture, the laws of physics as we know them are local features of one particular cosmic bubble, neither universal nor inevitable. The implications are philosophically vertiginous. If physical constants vary between universes, then the particular values that permit atoms, stars, planets, and observers to exist in our universe are not fine-tuned by design, but simply represent the range of conditions compatible with the existence of observers capable of asking the question. This is the anthropic principle applied at cosmological scale. Consider now the far future. If the universe continues to expand as current observations suggest, driven by dark energy, the structures we know will gradually dissipate. The stelliferous era, our current epoch, characterized by the formation and burning of stars, will give way over timescales of tens of trillions of years to the degenerate era, in which white dwarfs and neutron stars cool and dim. After that comes the black hole era, in which stellar mass black holes remain as the dominant complex structures, themselves slowly evaporating through Hawking radiation. The timescale for a stellar mass black hole to evaporate is approximately 10 to the 67th power years. For a supermassive black hole the size of M87's, the evaporation time is closer to 10 to
to the 100th power years, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. Eventually, the universe enters the dark era, a diffuse expanse of photons, neutrinos, and elementary particles, with no organized structures, no temperature gradients, and no mechanisms to drive complex processes of any kind.
But here, physics offers a strange and counterintuitive possibility. In a system with truly enough time, duration on scales that make the current age of the universe appear negligible, random quantum fluctuations can spontaneously assemble a localized region of lower entropy. The Poincaré recurrence theorem states that any bounded energy-conserving system will eventually return arbitrarily close to its initial state, given sufficient time. In a quantum context, similar recurrence applies. The timescale for a Poincaré recurrence in the post-heat-death universe, the time for the universe to spontaneously fluctuate back into a state resembling the early Big Bang, is incomprehensibly large but finite, and in an infinite future, finite probabilities, however small, become certainties. This idea was first articulated in a cosmological context by Ludwig Boltzmann, who recognized that his thermodynamic equations, while predicting that entropy overwhelmingly tends to increase, do not forbid its local temporary decrease. In an infinite system with infinite time, every configuration that is not strictly impossible will eventually occur. A rock, a planet, a galaxy, a star system with life. And most unsettling, a fully formed conscious mind, complete with memories of a past that never actually happened, assembled by chance from the ambient quantum foam. This is what has come to be called a Boltzmann brain, a self-aware entity that crystallizes spontaneously from a high-entropy background, believes itself to have a history, and then dissolves back into entropy moments later. The Boltzmann brain scenario creates a paradox. If Boltzmann brains are, across infinite time, more likely to spontaneously assemble than evolved observers like us are likely to emerge through biological processes, then by simple statistical reasoning, any given observer is more likely to be a Boltzmann brain than a genuine product of evolution, which raises the uncomfortable question: how would a Boltzmann brain know the difference? Its memories of a childhood, a history, a planet. All of these could be quantum accidents, internally consistent but cosmically counterfeit. The physicist André Linde captured the paradox with characteristic directness. If quantum field theory and inflationary cosmology are both correct, then the equations predict that in the infinitely extended future vacuum, new copies of any given observer's current mental state will continue to spontaneously arise. If that is true, then the current observer cannot determine whether they are an original or a copy, and the laws of physics, taken to their logical conclusions, undermine confidence in the observations on which those same laws are based. The deeper philosophical implication touches the nature of time itself. The second law of thermodynamics tells us that entropy increases with time, and this asymmetry is what gives time its direction. We remember the past and not the future, because the past was a state of lower entropy. But Boltzmann's insight suggests that the universe's current low entropy state is itself a fluctuation from a higher entropy background, a local accident in a vast equilibrium. If our observable universe is such an accident, then the direction of time, the nature of memory, and the reliability of scientific inference all rest on foundations that are contingent rather than necessary. This is either a sign that our theories need revision at their deepest level, or it is a genuine feature of reality. One so strange that even the most experienced cosmologists find it difficult to sit with comfortably. Among the observable universe's structures, dwarf galaxies occupy a peculiar position. They are simultaneously the most common type of galaxy and among the least understood. A dwarf galaxy might contain only a few 100 million stars, a number that sounds vast,
until compared with the hundreds of billions populating a large spiral galaxy like our own. Their surface brightnesses are low, their internal dynamics complex, and many of them are only detectable at all because modern observatories can register extraordinarily faint light across wide fields of view. The existence of dwarf galaxies is central to the story of how the universe built its large-scale architecture. Simulations of cosmic structure formation consistently predict that large galaxies like the Milky Way assembled hierarchically through repeated mergers of smaller systems, including many dwarf galaxy-scale progenitors. Most of this merging happened early, when the universe was less than a few billion years old. The evidence is written into the stellar populations and chemical abundances of large galaxies' inner regions. The thick disk and bulge of the Milky Way contain stellar populations with abundances and age distributions consistent with the absorbed remnants of dozens of ancient dwarf galaxies. The Gaia satellite, which has mapped the three-dimensional positions and velocities of over 1 billion stars in the Milky Way, has enabled the identification of several distinct stellar streams and substructures in the galaxy's halo, the kinematic fossils of ancient mergers. One prominent structure, called the Gaia sausage or Gaia Enceladus, represents the remnant of a dwarf galaxy, with a mass of several 100 million solar masses that merged with the Milky Way approximately 10 billion years ago, contributing many of the stars in the interstellar halo and possibly playing a role in the formation of the thick disk. Some dwarf galaxies present chemical puzzles that illuminate the very first generation of stars. The galaxy Segua 1, a dwarf spheroidal located only about 75,000 light-years from Earth and so faint that it was not catalogued until 2006, contains roughly 1,000 stars spread across a volume far larger than a globular cluster. Its stellar velocities imply the presence of an enormous dark matter halo. The galaxy's visible stars account for perhaps 0.1% of its total mass. Segway 1's stellar metallicity distribution spans several orders of magnitude, from stars barely enriched above the primordial hydrogen and helium composition of the universe to stars with somewhat higher metal content. This suggests its star formation history was extremely sporadic, possibly just one or two brief episodes, separated by long quiescent periods, before the galaxy was effectively sterilized, either by the radiation from the first massive stars or by the reionization of the intergalactic medium. Stars in such ultra-faint dwarfs may include some of the oldest stars in the observable universe, direct descendants of the very first stellar generation population 3 stars, whose deaths enriched the surrounding gas with the first heavy elements ever synthesized in stellar interiors. Those first stars, population 3, are among the most sought and least observed objects in astrophysics. They formed from primordial gas consisting almost entirely of hydrogen and helium, with no heavy elements to act as efficient coolants during gravitational collapse. Without metals, the gas could not fragment as efficiently, and the resulting stars are theorized to have been enormous, hundreds or even thousands of solar masses, burning hot blue and brief, exhausting their fuel in only a few million years before exploding as supernovae or collapsing directly into black holes. Their deaths seeded the surrounding medium with the first carbon, oxygen, silicon, and iron ever to exist in the universe. Elements that would go on to form the building blocks of subsequent generations of stars, planets, and eventually biology. No individual population 3 star has yet been directly observed, though the James Webb Space Telescope has detected candidate signatures of their collective radiation in the spectra of the most distant galaxies. Their black hole remnants, however, may be among the seed black holes from which the universe's first supermassive black holes grew, a chain of causation linking the death of the universe's first stars to the most massive objects in existence today. The galaxy Leo P, a dwarf irregular located roughly 5.3 million light-years away, provides a complementary case. Leo P is still forming stars today at a slow but measurable rate. Its extremely low metallicity reflects very little enrichment by heavy elements from previous stellar generations. Some of the lowest metallicity dwarfs known may be the closest surviving analogues to the very first galaxies, systems that began forming stars when the universe was only a few 100 million years old, in a cosmic environment so different from the present that comparison with modern large galaxies is almost misleading. Understanding these objects also means confronting the problem of missing satellites. Standard cosmological models predict that large galaxies should be surrounded by hundreds of dwarf satellites. The Milky Way has roughly 50 known dwarf companions, including the Magellanic Clouds and the host of ultra-faint systems discovered by wide field surveys. The discrepancy between prediction and observation has been debated for decades, with proposed resolutions ranging from observational incompleteness to physical mechanisms that suppress star formation in the smallest dark matter halos, leaving many potential dwarf galaxies as essentially invisible collections of dark matter with few or no stars. The satellite population of the Milky Way itself holds clues extending beyond the missing satellites problem. The large and small Magellanic Clouds, visible with the naked eye from the southern hemisphere as detached patches of the Milky Way, are interacting with each other and with the Milky Way in a complex gravitational ballet. The Magellanic Stream, a ribbon of gas stretching roughly 150 degrees across the sky, traces the material drawn out by tidal forces as the clouds orbit the Milky Way. The clouds are thought to be on their first close passage of the Milky Way, having arrived from intergalactic space relatively recently. Their future is uncertain. Some simulations suggest they will be absorbed into the Milky Way within a few billion years. Others indicate they may pass through and continue as independent systems. The outcome depends sensitively on the total mass of the Milky Way's dark matter halo, a quantity that remains uncertain to within a factor of 2, and which current and forthcoming astrometric surveys are working to constrain. The universe we have been describing has a shape. This fact is easy to state and surprisingly difficult to grapple with. The ancient intuition that the world was flat was not irrational. It was simply local. The curvature only became apparent when one began tracking ships disappearing hull first over the horizon, or measuring that the shadow Earth casts on the moon during a lunar eclipse is always circular, regardless of orientation, or eventually sailing around the planet. Similarly, determining the universe's global geometry requires looking beyond our immediate neighborhood at signals that carry information about structure on the largest scales. General relativity allows for 3 broad categories of spatial geometry. A positively curved universe would be finite and closed, like the 3-dimensional surface of a 4-dimensional sphere. In such a universe, parallel light beams would eventually converge, and a traveler moving in a straight line would eventually return to their starting point from the opposite direction. A negatively curved universe would be open and infinite, like the surface of a saddle extended to infinite extent, with parallel beams diverging forever. In the flat universe, the critical case would have parallel beams remaining parallel indefinitely, with the familiar geometry of Euclid applying on cosmic scales. The cosmic microwave background provides our most precise measurement of cosmic geometry. Acoustic oscillations in the early universe's plasma, driven by the competing forces of gravity pulling matter together and radiation pressure pushing it apart, imprinted a characteristic pattern of temperature fluctuations on the CMB at specific angular scales. The position of the first acoustic peak in the CMB power spectrum is sensitive to the universe's spatial curvature. Data from the Planck satellite place the first acoustic peak at an angular scale of approximately 1 degree, entirely consistent with the flat geometry, The resulting constraint on the universe's curvature is among the tightest measurements in all of cosmology, ruling out significant positive or negative curvature to a precision of about 0.5%.
These same acoustic oscillations left a second imprint that can be detected not only in the CMB, but in the large-scale distribution of galaxies today. The baryon acoustic oscillation, a preferred separation distance of roughly 500 million light-years between pairs of galaxies corresponding to the sound horizon of the early universe, functions as a standard ruler. By measuring this preferred scale at different distances and therefore different epochs of cosmic history, astronomers can trace the expansion history of the universe with precision comparable to supernova surveys. The combination of baryon acoustic oscillations, CMB measurements, and supernova distances has produced the current concordance cosmological model, a universe that is 68% dark energy, 27% dark matter, and only about 5% ordinary baryonic matter. Flat, however, does not mean simple. A flat universe can still have a non-trivial topology. A universe with a toroidal topology could be flat and yet finite. Travel far enough in one direction and you return to your starting point. Searches for this topology in the CMB have been conducted by looking for matched patterns on opposite sides of the sky. So far, no such signature has been confirmed. But the absence of evidence is not evidence of absence at cosmological scales, and the search continues. Between the shape of the universe and the structures it contains lies one of the most awe-inducing features of modern cosmology, the cosmic web. Matter in the universe is not distributed uniformly. It is arranged in a vast three-dimensional network of filaments, sheets, and nodes, with enormous voids occupying the spaces between. Galaxies cluster along the filaments with the densest concentrations at the intersections where multiple filaments converge. The voids between filaments are not truly empty, but their galaxy density is so low compared to the surrounding structure that they appear, on large-scale maps, as dark bubbles tens or hundreds of millions of light-years across. The Boötes void is among the largest of these underdensities, a roughly spherical region approximately 330 million light-years in diameter, lying about 700 million light-years from Earth. Discovered in 1981 during a survey of galaxy redshifts, its sheer emptiness initially struck astronomers as almost inexplicably large. Standard models of structure formation predict that voids this size should be rare at this cosmic epoch. More recent surveys have found several comparably sized voids, suggesting that the Boötes void is unusual but not anomalous. Still standing metaphorically at its center, one would see almost no galaxies in any direction for hundreds of millions of light-years. A silence in the cosmic landscape that has no analog in human experience. At the opposite extreme are the superclusters, the largest coherent structures in the observable universe. The Milky Way sits within the local group, a modest assembly of roughly 80 galaxies dominated by the Milky Way and the Andromeda Galaxy. The local group, in turn, belongs to the gravitational sphere of influence of the Virgo cluster. Beyond that lies the Laniakea supercluster, a structure identified in 2014 by Brent Tully and colleagues, who used measurements of galaxy velocities to trace the boundaries of a coherent gravitational basin spanning roughly 520 million light-years and containing approximately 100,000 galaxies. The Milky Way lies near the outer edge of this structure, moving slowly toward its center of mass, a region of enhanced density known as the Great Attractor. But even Laniakea is not the deepest gravitational basin in our part of the universe. Beyond the Great Attractor lie the Shapley supercluster, located approximately 650 million light-years away, and in the opposite direction, a structure of negative influence.
the dipole repeller a supervoid whose relative absence of matter effectively pushes our local group away from it.
Because galaxy clusters pull galaxies toward them through gravity, and voids push them away by their relative absence of gravitational pull. The cosmic flows that move entire superclusters across intergalactic space are shaped not only by what is present, but by what is absent. The universe's architecture is defined by both its mountains and its valleys. Mapping these flows requires measuring not just the positions of hundreds of thousands of galaxies, but their velocities, the component of motion that is not simply cosmic expansion, but genuine peculiar motion through space, driven by local gravitational forces. This requires redshift surveys of extraordinary completeness, because missing galaxies, particularly those hidden behind the obscuring dust of our own Milky Way in the so-called zone of avoidance, create blind spots in the flow maps. Radio surveys, which penetrate the dust that blocks optical wavelengths, have been essential in revealing the structure of the Great Attractor region and confirming the scale of the Shapley concentration. The Shapley supercluster contains mass estimated at some 50 million billion solar masses, with a clumped structure of rich galaxy clusters embedded in a broader enhancement of galaxy density, a gravitational mountain that shapes the flow of the surrounding universe across scales of hundreds of millions of light years. The deepest mystery is not what the universe contains, but how much of it we can never see. Our observational reach is finite, bounded not by telescope aperture, but by the speed of light and the age of the universe. The most distant light we can receive has been traveling for 13.8 billion years. But because space itself has been expanding during that time, the objects that emitted the light we see at the edge of our observable universe are now roughly 46 billion light years away. Our observable universe is a sphere of that radius centered on us. Looking outward is looking backward in time. The star Deneb in the constellation Cygnus lies approximately 2,600 light years away. The light by which we see it tonight left it approximately 2,600 years ago, when the Achaemenid Empire was approaching its height. The Andromeda Galaxy, our nearest large spiral neighbor, lies about 2.5 million light years away. Every photon arriving from it tonight has been traveling since before the genus Homo existed on Earth. The galaxy NGC 4889, the brightest member of the Coma cluster, is roughly 308 million light years away. Its light left when the Permian period was ending in one of the greatest mass extinctions in Earth's history. Scale further, the quasar PKS 2000 330, at a redshift placing it approximately 12 billion light years away as light travel distance, was observed as it existed when the universe was less than 2 billion years old, when the Milky Way was still assembling, when our Sun did not yet exist as so much as a molecular cloud. There is an important distinction between the particle horizon and the event horizon of the universe. The particle horizon marks the edge of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang. The event horizon of the universe, by contrast, marks the farthest distance from which light emitted today will ever reach us, taking into account the accelerating expansion. Because dark energy is causing the expansion to accelerate, regions currently beyond about 16 billion light years are receding faster than light, and signals they emit now will never reach the Milky Way. The universe has an event horizon in this cosmological sense, a boundary beyond which information is being permanently cut off as the expansion sweeps it away. Every year, new regions of the universe cross this horizon and become permanently inaccessible. The observable universe is not shrinking in an absolute sense. New ancient light continues to arrive as we look deeper. But in terms of what we can ever influence or receive signals from, our causal reach is contracting. The deepest signal we can receive from the early universe is the cosmic microwave background. Light emitted when the universe was approximately 380,000 years old, at the moment when the plasma of the early cosmos cooled enough to become transparent. That light arrives at our detectors redshifted from its original temperature of nearly 3000 Kelvin to a current temperature of just 2.7 Kelvin above absolute zero, a quiet, pervasive hiss of microwave radiation that fills the sky with extraordinary uniformity. Those tiny temperature fluctuations at the level of 1 part in 100,000 are the seeds from which all cosmic structure grew. Before the CMB, before the universe became transparent, there is a wall of opacity through which no electromagnetic radiation from that era can penetrate. But gravity is not blocked. Gravitational waves propagate freely through any medium. The detection of primordial gravitational waves imprinted by inflation on the polarization pattern of the CMB would open a window onto epochs before recombination, before nucleosynthesis, before the first second of cosmic time. The search for this signal, called the B-mode polarization, has been underway for years at facilities, including the South Pole Telescope and the B-SEP array. Its detection would be among the most consequential events in the history of science. Beyond the CMB wall lies the cosmic dark age, the epoch before the first stars lit up, a period of several 100 million years during which the universe was filled with neutral hydrogen and helium, but no sources of light. This era ended with the epoch of reionization, when the first massive stars and the first quasars flooded the universe with ultraviolet radiation, stripping electrons from the ambient neutral gas and making the intergalactic medium transparent again. The James Webb Space Telescope has detected individual galaxies forming during this reionization epoch, objects whose light has traveled to us for more than 13 billion years and arrives still carrying information about a cosmos almost unrecognizably different from the one we inhabit. Dark matter runs through every level of this structure. We cannot see it directly, it does not emit, absorb, or scatter light, but its gravitational effects are unmistakable. In the rotation curves of galaxies, in the velocities of galaxies within clusters, in the large-scale pattern of the cosmic web, and in the detailed structure of the CMB power spectrum. The distribution of dark matter acts as a scaffold. Ordinary matter falls into the gravitational wells that dark matter creates, and the visible universe of stars and gases, in a real sense, the luminous foam floating on an invisible ocean. The leading candidate for decades was the WIMP, the weakly interacting massive particle, a hypothetical elementary particle whose predicted abundance in the early universe matches the observed amount of dark matter with remarkable precision. But decades of underground experiments, particle collider searches, and space-based observations designed to detect WIMPs have returned nothing definitive. Alternative candidates, exons, sterile neutrinos, primordial black holes, each have their advocates and their dedicated searches. Dark matter remains the most precisely characterized unknown substance in the history of science. Dark energy is, if anything, even more mysterious. The discovery in 1998 that the universe's expansion is accelerating rather than decelerating under the influence of gravity, as had been expected, was awarded the Nobel Prize in Physics and constituted one of the most startling results in modern cosmology. Something is driving the accelerated expansion. The simplest explanation is a cosmological constant, a uniform energy density inherent to empty space itself, first introduced by Einstein in a different context. Current observations are consistent with a cosmological constant, but quantum field theory predicts that vacuum energy should be many orders of magnitude larger than what we observe, and no known physical mechanism explains why it is so small while still being non-zero. This is the cosmological constant problem, and it remains without a satisfying resolution.
What we have traced in this account, from the spin of individual black holes to the gravitational pull of superclusters, hundreds of millions of light years away, is only one layer of a deeper structure that we are only beginning to map. The universe has a hierarchy. At its smallest scales, elementary particles interact through four fundamental forces. At the scale of stars, nuclear physics governs energy generation and determines how a star burns and how it ends. At the scale of galaxies, the interplay between ordinary matter, dark matter, and the radiation field of active galactic nuclei regulates star formation and chemical evolution. At the scale of superclusters and the cosmic web, gravitational dynamics and the large-scale geometry of space-time determine how matter flows and congregates over billions of years.
And at the larger scales, the expansion history of the universe, governed by dark energy, determines whether structures continue to form or whether the accelerating expansion eventually tears apart every bound system, in a scenario called the Big Rip. The James Webb Space Telescope has begun to challenge some assumptions about how early in cosmic history galaxies formed and grew massive. Multiple candidate galaxies have been identified at redshifts suggesting they existed when the universe was only 300 to 400 million years old, and several appear surprisingly massive and structured for their age, more developed than standard models predicted. Whether this represents a genuine challenge to the current cosmological model or simply reflects the natural variance in early galaxy formation is still being evaluated. But it is a reminder that our models, however successful on large scales, are still being tested against the universe's actual behavior at the extremes of space and time. Every instrument that has pushed the frontier further, from Galileo's telescope to the Hubble Space Telescope to the Event Horizon Telescope to the gravitational wave detectors of LIGO and Virgo, has revealed that the universe is stranger, more varied, and more richly structured than the previous generation of scientists suspected. The pattern is consistent, and there is no reason it should stop. The questions we cannot yet ask, because we lack the instruments or the theoretical frameworks to formulate them, may prove to be the most important questions of all. Science at its best is not the accumulation of answers, but the progressive refinement of questions, and the universe, patient and indifferent, continues to supply material for that refinement at a rate we have never quite managed to exhaust. We stand at the edge of what we can see, looking outward into the unobservable, surrounded by a cosmos whose full extent we will never measure, asking questions that may have no answers within any horizon we can reach. That this situation is frustrating is obvious. That it is also magnificent seems, on reflection, equally true. Among the most extreme objects in the universe, black holes share the stage with a close relative that is, in many ways, equally astonishing: the neutron star. When a massive star exhausts its nuclear fuel and its core collapses, the outcome depends on the mass of that core. If the core exceeds roughly 3 solar masses, nothing can halt the collapse. It continues until a black hole forms. But for cores between approximately 1.4 and 3 solar masses, the collapse is arrested by neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids 2 neutrons from occupying the same quantum state simultaneously. The result is a neutron star, an object with roughly the mass of the Sun compressed into a sphere about 20 kilometers across, with a density exceeding that of an atomic nucleus. A teaspoon of neutron star material would weigh roughly 10 million tons on Earth's surface. Neutron stars rotate. When a massive star collapses, conservation of angular momentum causes the rotation rate to increase dramatically, in the same way that a spinning ice skater accelerates when they draw their arms inward. A star that rotated once per month before collapse may rotate hundreds of times per second after it.
These rapidly rotating neutron stars, called pulsars, emit beams of electromagnetic radiation from their magnetic poles, sweeping through space like cosmic lighthouses. When these beams are oriented to sweep across Earth, we detect regular pulses of radio waves with extraordinary precision. The pulsar PSR J1748D2446AD, discovered in 2004, rotates approximately 716 times per second, its surface moving at nearly a quarter of the speed of light.
The regularity of pulsar timing rivals the best atomic clocks on Earth, making pulsars among the most precise natural timekeepers in the universe. This precision has been turned into a tool for fundamental physics. Binary pulsar systems, where two neutron stars orbit each other, provide laboratories for general relativity in the strong field regime. The first binary pulsar, PSR B1913+16, was discovered by Russell Holtz and Joseph Taylor in 1974. Over decades of observation, the orbital period of this system was found to be shrinking at exactly the rate predicted by general relativity. If the system were losing energy by emitting gravitational waves, this was the first indirect detection of gravitational waves, and it earned Holtz and Taylor the Nobel Prize in Physics in 1993. Decades later, in 2017, the merger of two neutron stars, the event GW170817, was detected directly by LIGO and Virgo, and the resulting electromagnetic counterpart was observed simultaneously by telescopes across the globe. For a fraction of a second, this event outshone the entire galaxy in which it occurred. It produced gravitational waves, a burst of gamma rays, a kilonova, a transient optical source powered by the radioactive decay of heavy elements synthesized in the merger, and crucially direct evidence that neutron star mergers are a primary site of our process, nucleosynthesis, the rapid capture of neutrons that produces the heaviest elements in the periodic table, including gold, platinum, and uranium. Every piece of gold ever mined on Earth was forged in a neutron star collision that predated the formation of the solar system. Magnetars represent the most extreme variety of neutron stars, objects with magnetic fields trillions of times stronger than Earth's and quadrillions of times stronger than the most powerful laboratory magnets ever built. The magnetic field of a magnetar is so intense that it affects the quantum structure of the vacuum itself, distorting the electron clouds around atoms and altering the way light propagates through the surrounding space. Magnetar flares, violent reorganizations of the magnetic field, release more energy in a fraction of a second than the sun emits in tens of thousands of years. A magnetar flare from SGR 620, located about 50,000 light-years from Earth, swept through the solar system in December 2004 and briefly ionized the upper atmosphere of Earth despite its enormous distance. Were such a magnetar located within a few light-years of Earth, its flares would strip the atmosphere and sterilize the surface. The universe contains objects at every scale of violence, from the gentle glow of red dwarf stars to the cataclysmic outbursts of magnetars. And each sits within a continuous spectrum of physical extremity that extends from the nearly imperceptibly subtle to the cosmically catastrophic. Gamma-ray bursts occupy the far end of that spectrum among detectable transient events. They are among the most energetic explosions in the observable universe, releasing more energy in a matter of seconds than the sun will emit over its entire 10 billion year lifetime. They were discovered accidentally in the late 1960s by American military satellites designed to monitor compliance with the Nuclear Test Ban Treaty. The satellites detected brief bursts of gamma radiation coming not from Earth, but from deep space. Decades of subsequent observation have established that gamma-ray bursts come in two varieties: long bursts lasting more than 2 seconds and associated with the collapse of massive stars, the same events that produce some supernovae, and short bursts lasting less than 2 seconds and associated with the mergers of compact objects such as two neutron stars
or a neutron star and a black hole.
The afterglow of a gamma-ray burst, the longer wavelength radiation that persists for hours, days, or weeks as the relativistic jet from the explosion sweeps through the surrounding medium, can be detected at cosmological distances, making gamma-ray bursts among the most powerful probes of the high redshift universe. The most distant gamma-ray burst yet detected, GRB 090423, occurred at a redshift of approximately 8.2, meaning the light we detected left the explosion when the universe was only about 630 million years old, making it one of the most distant individual events ever observed. The life cycle of stars encompasses an enormous range of outcomes, depending primarily on mass. Stars with less than about 0.08 solar masses never achieve the core temperatures necessary to ignite hydrogen fusion. They are brown dwarfs, neither quite stars nor quite planets, glowing faintly from the heat of their gravitational contraction. Stars between roughly 0.08 and 0.3 solar masses are red dwarfs, dim, cool, and extraordinarily long-lived. A red dwarf with half the mass of the Sun will burn for trillions of years, long after the Sun itself has died. Because the universe is only 13.8 billion years old, no red dwarf has yet reached the end of its life. Every red dwarf that has ever formed still exists. They are the dominant stellar type in the galaxy, making up roughly 70 to 75% of all stars, and their longevity makes them the most plausible hosts for planets with long-lived complex biospheres. Stars between roughly Boyd-free and 8 solar masses, including our Sun, spend most of their lives burning hydrogen in their cores on the main sequence, then swell into red giants as their hydrogen is exhausted and helium fusion commences. The outer layers are eventually expelled as a planetary nebula, a glowing shell of gas lit by the ultraviolet radiation of the hot remnant at its center. What remains is a white dwarf, the inert carbon-oxygen core of the former star, roughly the size of Earth, cooling slowly over billions of years. The Ring Nebula in the constellation Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco. These are all dying stars caught in the act of shedding their outer layers, each one a preview of the Sun's fate approximately 5 billion years from now. When the Sun eventually swells into a red giant, approximately 4.5 to 5 billion years from now, it will expand to a radius roughly 100 to 200 times its current size, engulfing Mercury, Venus, and possibly Earth in the process, though uncertainties in the model leave Earth's fate ambiguous. The details depend sensitively on the rate of mass loss during the red giant phase, which changes the Sun's gravitational hold on the Earth and may allow Earth's orbit to migrate outward fast enough to escape engulfment. In any case, the inner solar system will be rendered uninhabitable long before the Sun reaches its maximum radius. As the Sun's luminosity increases over the next billion years, surface temperatures on Earth will rise until the oceans boil. Life on Earth, if it persists, will likely need to migrate elsewhere, or the planet will need to be artificially repositioned. These are not urgent concerns, but on cosmic timescales, they are not distant ones either. The Milky Way itself is on a collision course with the Andromeda Galaxy, our nearest large spiral neighbor, currently approaching at roughly 1110 kilometers per second. In approximately 4.5 billion years, the two galaxies will make their first close approach. The collision will not be a simple impact. Galaxies are mostly empty space, and the individual stars within them are unlikely to collide directly. Instead, the two galaxies will interpenetrate, their gravitational interactions distorting their spiral structures, generating long tidal tails of stars drawn out into intergalactic space, triggering bursts of star formation as gas clouds are compressed by the encounter. Over the following few billion years, after multiple close passages,
The two galaxies will merge into a single elliptical galaxy, sometimes called Milkomeda or Milkdromeda in informal discussions. The Sun may be flung to a very different orbital radius during this process, potentially to the outer reaches of the merged system.
The night sky during the merger, as seen from any surviving planetary surface, would be spectacular beyond any current analog. A chaotic blaze of disturbed stars and luminous tidal structures, visible even in daylight. The Andromeda Galaxy itself is not the only large member of the local group. The Triangulum Galaxy, M33, is the third largest member, a smaller spiral located about 2.7 million light-years away. The broader local group also contains several dozen dwarf galaxies, most of them satellites of either the Milky Way or Andromeda. Beyond the local group, the nearest comparable structure is the M81 group, centered on the spiral galaxy Messier 81 in Ursa Major, approximately 12 million light-years away. The nearest large galaxy cluster is the Virgo cluster, approximately 54 million light-years away, containing over 1,300 confirmed member galaxies and exerting gravitational influence across a sphere of tens of millions of light-years. Cosmic rays represent another window on the universe's most extreme processes, one that predates modern gamma-ray and gravitational wave astronomy. Cosmic rays are high-energy subatomic particles, primarily protons and atomic nuclei, that rain down on Earth's atmosphere continuously from all directions. They were discovered in 1912 by Victor Hess during a series of balloon flights in which he measured ionizing radiation at high altitudes and found it increased rather than decreased with altitude, demonstrating that the source was extraterrestrial. The energy spectrum of cosmic rays spans an enormous range, from energies achievable by solar flares to energies so extreme that a single particle carries the kinetic energy of a well-hit baseball compressed into a proton.
Ultra-high energy cosmic rays, those above 10 to the 19th electron volts, are of unknown origin. They are rare, only a handful are detected per square kilometer per century. At these energies, particles interact with the cosmic microwave background radiation through a process called the GZK effect, named after Greisen, Satzepin and Kuzmin, who predicted in 1966 that protons with energies above roughly 5 times 10 to the 19th electron volts would be quickly degraded by interactions with CMB photons.
This means ultra-high energy cosmic rays must have originated relatively nearby, within roughly 100 to 200 million light-years, because more distant sources would be degraded below this energy threshold before reaching Earth. The identity of the astrophysical objects accelerating particles to these extreme energies remains one of the outstanding open questions in high-energy astrophysics, with candidate sources including gamma-ray burst jets, the vicinity of active galactic nuclei, and the termination shocks of powerful radiogalaxy lobes. The interstellar medium, the gas and dust that fills the space between stars within a galaxy, is a vastly more complex and dynamic environment than its apparent emptiness might suggest. It is not uniform. It exists in several distinct phases, ranging from hot, tenuous plasma heated to millions of degrees by supernova shockwaves and the winds of massive stars, through warm ionized gas and warm neutral gas, to cold, dense molecular clouds, where temperatures drop to only 10 or 20 Kelvin and densities reach thousands of atoms per cubic centimeter. These molecular clouds, most prominently visible as dark nebulae silhouetted against the background glow of the Milky Way, are the birthplaces of stars. Within them, turbulence, magnetic fields, and self-gravity compete to determine which regions will collapse and which will be held up. The Orion molecular cloud, at a distance of about 1,344 light-years and spanning roughly 100 light-years across, contains many thousands of solar masses of gas and is actively forming stars at multiple sites, including the famous Orion Nebula, a stellar nursery where hot young stars are eroding their birth cloud with ultraviolet radiation, sculpting dramatic pillars and cavities visible even through small telescopes. The chemistry of the interstellar medium has proven to be extraordinarily rich. Radio astronomers, using the techniques of molecular spectroscopy, have identified over 200 distinct molecular species in interstellar space, including complex organic molecules such as glycolaldehyde, a simple sugar, and ethyl formate, one of the compounds responsible for the smell of raspberries. These molecules form on the surfaces of interstellar dust grains in the cold cores of molecular clouds, then are liberated into the gas phase when surrounding protostars heat the cloud. The presence of complex organic chemistry in interstellar space implies that the raw chemical ingredients for life, or at least for life's precursors, are widely distributed throughout the galaxy, delivered to planetary surfaces by comets and asteroids during the early bombardment phases of solar system formation. This has bearing on one of the deepest questions any of this knowledge leads toward, whether life is unique to Earth or distributed throughout the universe. The discovery of exoplanets, planets orbiting stars other than the Sun, has transformed this question from purely philosophical to empirically tractable. Before 1992, no confirmed exoplanet existed. By 2024, over 5,500 had been confirmed, with thousands more awaiting confirmation. The Kepler Space Telescope, which operated from 2009 to 2018, surveyed approximately 530,000 stars and found that planets are not rare exceptions but common outcomes of stellar formation. Statistical analysis of the Kepler data suggests that the Milky Way contains at least as many planets as it does stars, perhaps hundreds of billions. Rocky planets in the habitable zones of their host stars, regions where liquid water could exist on the surface, are found around a significant fraction of Sun-like stars. The TRAPPIST-1 system, a red dwarf star about 40 light-years away, harbors 7 Earth-sized planets, 3 of which orbit within the habitable zone. Whether any of these worlds hosts life is unknown. The atmospheric characterization of exoplanets, measuring the composition of their atmospheres by analyzing the starlight that filters through them during transits, is now underway, with the James Webb Space Telescope detecting atmospheric signatures around planets, including those in the TRAPPIST-1 system. The question of whether life exists elsewhere in the universe is connected to some of the deepest uncertainties in biology, chemistry, and planetary science. The origin of life on Earth, the transition from chemistry to biology, from replicating molecules to cellular organisms, is not understood in detail. We do not know whether it is a common outcome under the right physical and chemical conditions, or whether it required a sequence of improbable events that may have occurred only once. The amino acids and nucleobases found in carbonaceous meteorites demonstrate that the molecular building blocks of life are synthesized abiotically in space. Whether these building blocks are sufficient, whether liquid water and an energy source are necessary, whether the genetic code that life on Earth uses is one of many possible solutions, or effectively the only viable one. All of these questions remain open. The detection of a single confirmed example of life elsewhere in the universe, even microbial life, even fossilized evidence of past life, even the atmospheric signature of a biosignature gas in an exoplanet spectrum, would transform every answer we might give to every question posed in this account. Gravitational waves have opened an entirely new observational channel to the universe,
one that complements electromagnetic astronomy in ways that are still being explored.
The LIGO detectors measure changes in the length of 4-kilometer laser interferometer arms caused by passing gravitational waves. The strains involved are almost incomprehensibly small. The first detected gravitational wave event, GW150914, caused the arms to stretch and compress by roughly 1,000th the diameter of a proton. This detection, announced in February 2016, confirmed a prediction of general relativity that had stood for a century without direct verification and inaugurated the era of gravitational wave astronomy. In the years since, LIGO and its partner detector Virgo have detected dozens of gravitational wave events, black hole mergers, neutron-star mergers, and events of uncertain classification, each providing information about the masses, spins, and distances of compact objects that electromagnetic observations alone could not determine. The planned laser interferometer space antenna, a space-based gravitational wave detector consisting of 3 spacecraft in a triangular formation with arm lengths of 2.5 million kilometers, will be sensitive to lower frequency gravitational waves than ground-based detectors can reach, enabling the detection of supermassive black hole binary mergers across the observable universe and potentially the stochastic gravitational wave background from inflation itself. The universe disclosed by all of these methods, electromagnetic astronomy across the full wavelength range from radio to gamma rays, gravitational wave detection, cosmic ray measurements, and neutrino astronomy, is one of almost overwhelming complexity and scale. Its hierarchical structure, from quarks to atoms to stars to galaxies to the cosmic web, is governed by a set of physical laws whose parameters appear within the precision of our measurements, to be exquisitely tuned to permit the existence of the complexity we observe. Whether this apparent fine-tuning reflects a deeper physical principle, the selection effect of our own existence within a multiverse of varied conditions, or simply the incompleteness of our current understanding, is a question that touches the deepest foundations of science. What does seem clear is that the universe is not merely a backdrop for the drama of human existence. It is itself the drama, evolving, structured, violent, ancient, and in many respects still profoundly unknown. The 13.8 billion years that separate us from the Big Bang have produced an observable cosmos containing roughly 2 trillion galaxies, each containing hundreds of billions of stars, each star a thermonuclear reactor held together by its own gravity, each planetary system a unique laboratory of chemistry and physics, each atom in every object an artifact of processes that began in the first seconds of time and have continued through every stellar birth and death since. We are assembled from the same processes, from carbon forged in stellar cores, from oxygen expelled in stellar winds, from iron dispersed by ancient supernovae. When we attempt to understand the universe, we are, in a sense, the universe attempting to understand itself. The fact that this attempt is possible at all, that the laws of physics permit minds complex enough to discover those laws, is perhaps the deepest strangeness of all. It is not guaranteed by anything we know. It is not predicted by the equations. It is simply a feature of the universe we happen to inhabit, that its structure, from the first quantum fluctuation in the inflationary epoch to the last photon emitted by an evaporating black hole in the unimaginably distant future, is comprehensible, imperfectly, provisionally, incrementally comprehensible, but comprehensible nonetheless. That is the most remarkable fact about the universe. And it is also the reason this account can exist at all. We stand at the edge of what we can see, looking outward into the unobservable, surrounded by a cosmos whose full extent we will never measure, asking questions that may have no answers within any horizon we can reach.
Every era of astronomy has been characterized by a horizon beyond which we could not see, and every generation of new instruments has pushed that horizon further back, revealing structures and phenomena that no one anticipated. There is no reason to believe this process has reached its conclusion. The universe has consistently demonstrated that it contains more than we expected. It appears determined to continue doing so. To make sense of the universe's history requires understanding not just what it contains, but how it has changed over time. The universe today is profoundly different from the universe of 10 billion years ago. And that universe was profoundly different from the universe of 1 billion years after the Big Bang. The cosmic history can be read in several overlapping ways, through the spectra of distant objects which carry information about their chemical composition at the time the light was emitted, through the redshifts of galaxies which encode their distances and the epoch at which we observe them, through the CMB which provides a snapshot of conditions 380,000 years after the Big Bang, and through gravitational waves which travel unimpeded from the earliest moments of structure formation. One of the most striking features of this history is the peak of cosmic star formation. The universe was forming stars at a far higher rate when it was 2 to 3 billion years old than it is today. This period of peak star formation, sometimes called cosmic noon, saw enormous quantities of gas collapsing into galaxies and forming stars at rates 10 to 20 times higher than the present global average. The reasons for this peak and subsequent decline are multiple. The supply of cold gas available for star formation has been gradually consumed and heated over cosmic time. The feedback from active galactic nuclei has expelled and heated gas in massive galaxies, quenching their star formation, and the overall density of the universe has declined as expansion continues, making gravitational collapse progressively less efficient. The result is a universe that was, in its youth, a far more violent and productive place than it is today, a point worth remembering when contemplating the relative calm of the present Milky Way. The chemical evolution of the universe follows a similar arc. The first stars, population 3, formed from essentially pure hydrogen and helium. When they died, they enriched the surrounding medium with the first heavy elements. The next generation of stars, population 2, formed from this slightly enriched gas, and their deaths produced further enrichment. Today's stars, population I, including the Sun, form from gas that has been processed through multiple stellar generations, and their chemical abundances reflect billions of years of cumulative nucleosynthesis. The oldest stars in the Milky Way's halo, with metallicities hundreds of times lower than the Sun's, carry within their atmospheres a chemical record of the first stellar generations, a kind of archaeology conducted in spectral lines rather than buried artifacts. Some stars have metallicities so low that they must have formed within the first few 100 million years of cosmic history, preserving the imprint of the very first supernovae. The interplay between star formation and chemical enrichment is embedded in a broader ecosystem. The baryon cycle. Gas falls into galaxies from the cosmic web, forms stars. Those stars produce energy and heavy elements. Stellar winds and supernovae expel gas back into the circumgalactic medium and beyond. That gas cools and falls back in, and the cycle repeats. Active galactic nuclei inject additional energy into this cycle, capable of heating or ejecting gas over scales far larger than any stellar process. The circumgalactic medium, the extended halo of diffuse gas surrounding a galaxy, typically extending to hundreds of thousands of light years, serves as the reservoir and the regulator. It is both the fuel tank from which galaxies draw their gas and the exhaust system into which they expel their waste products. Understanding the baryon cycle in detail, how efficiently gas flows in and out, how effectively supernovae and AGN heat and expel it, how the metallicity of the circumgalactic medium changes over time is one of the central challenges of contemporary galaxy formation theory. The cosmic web itself encodes the initial conditions of the universe.
The pattern of filaments and voids is not random. It is a direct consequence of the primordial density fluctuations left by inflation and amplified by gravity over billions of years. The statistics of the large-scale distribution of galaxies measured through surveys like the Sloan Digital Sky Survey, the Dark Energy Spectroscopic Instrument, and the forthcoming Euclid space mission carry information about the amplitude and shape of those primordial fluctuations, about the amount of dark matter and dark energy, about the sum of neutrino masses, and about the detailed properties of the inflationary epoch. The Sloan Digital Sky Survey, which over its lifetime has mapped the positions and spectra of millions of galaxies across a significant fraction of the sky, revealed spectacular large-scale structures including the Sloan Great Wall, a sheet of galaxies approximately 1.37 billion light-years long, one of the largest known structures in the observable universe. The Hercules Corona Borealis Great Wall, identified in 2013 from the distribution of gamma-ray bursts at high redshift, spans an estimated 10 billion light-years, a size that, if confirmed, challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales. At 10 billion light-years, this structure would encompass a significant fraction of the observable universe, suggesting that our models of cosmic structure may need refinement on the very largest scales. Understanding these structures requires not just cataloging them, but measuring the velocities of their constituent galaxies, distinguishing the motion due to cosmic expansion from peculiar motions driven by local gravitational forces. This peculiar velocity field encodes the mass distribution of the universe in a way that complements direct measurements of galaxy positions. The comparison between the peculiar velocity field inferred from galaxy surveys and the predictions of the current cosmological model provides one of the most stringent tests of that model on large scales. Discrepancies, and there are hints of possible tensions between different datasets, may point toward physics beyond the standard model. Modifications to gravity on large scales, properties of dark energy that vary with time or direction, or statistical fluctuations in a universe that is, at the end of the day, a single realization of a stochastic process. The tension in the Hubble constant is perhaps the most discussed of these potential discrepancies. The Hubble constant, the rate at which the universe is currently expanding, can be measured in multiple independent ways. The value inferred from the CMB, assuming the standard cosmological model, is approximately 67.4 kilometers per second per megaparsec. The value inferred from the local distance ladder, measurements of Cepheid variable stars and type AEA supernovae in nearby galaxies, is approximately 73 kilometers per second per megaparsec. The difference between these two values is statistically significant, now exceeding 5 standard deviations, a level at which physicists typically declare a genuine discrepancy rather than a statistical fluctuation. Whether this tension reflects a systematic error in one or both measurements, or genuine new physics beyond the standard cosmological model, early dark energy, additional relativistic species in the early universe, modifications to gravity, is a question that the next generation of observational programs is urgently attempting to answer. If the Hubble tension is real and requires new physics, the implications for our understanding of the universe's content and history would be profound. These tensions and uncertainties are not signs of failure. They are signs of a science in active contact with reality, a discipline that has made enough progress to identify where its current best models are strained, and that has the observational tools to probe those strains with increasing precision. The history of cosmology is littered with discarded models that once seemed secure: the static universe, the steady-state model, the assumption that the expansion was decelerating. Each time a model was overturned,
It was not because science had failed, but because science had succeeded, because observations had reached the precision necessary to detect the ways in which the model was incomplete. The Hubble tension, the anomalies in the CMB, the excess of massive early galaxies detected by GWST, each is an invitation. The universe is pointing at something we have not yet understood, and the history of the discipline gives every reason to expect that understanding it will lead somewhere remarkable. The tools available for this investigation are more powerful than at any previous moment in history. The Vera-C, Rubin Observatory, currently undergoing commissioning in Chile, will conduct the Legacy Survey of Space and Time, a 10-year program that will image the southern sky repeatedly, generating a movie of the variable and transient universe, and cataloging billions of galaxies, millions of supernovae, and the detailed photometric properties of the solar system's small body population. The Square Kilometre Array, a network of radio dishes and aperture arrays distributed across South Africa and Australia, will map the hydrogen gas content of galaxies across cosmic time, detect gravitational wave backgrounds through pulsar timing, and probe the epoch of reionization with sensitivity orders of magnitude beyond current instruments. The Nancy Grace Roman Space Telescope will conduct a wide-field infrared survey of the sky, measuring baryon acoustic oscillations and weak gravitational lensing across volumes of the universe never before accessible in a single survey. And in the longer term, the Laser Interferometer Space Antenna will open the millihertz gravitational wave band, giving access to supermassive black hole mergers, compact binary in spirals throughout the Milky Way, and potentially the stochastic gravitational wave background from the earliest moments of the universe. Each of these instruments is designed to push against a specific frontier: the nature of dark energy, the history of cosmic structure, the demographics of compact objects, the properties of the early universe. Together they represent the most comprehensive, coordinated program of cosmic investigation ever attempted. The questions they are designed to answer: what is dark energy? How do supermassive black holes grow? How did the first galaxies form? What is the sum of neutrino masses? Does the universe have a non-trivial topology? Are among the deepest questions in physics. Some may be answered within decades. Others may prove to require observational or theoretical breakthroughs that are not yet imaginable. What remains constant across all of this is the scale and the strangeness. The universe contains roughly 2 trillion galaxies. Each galaxy contains on average several 100 billion stars. Each star is a self-gravitating thermonuclear reactor, typically burning for billions to hundreds of billions of years. The energy released by stars over the history of the universe is staggering beyond any conventional analogy. The heavy elements produced in those stars, carbon, nitrogen, oxygen, silicon, iron, and all the rest, have been distributed through the interstellar medium by stellar winds, supernovae, neutron star mergers, and the tidal disruption of stars by black holes, eventually condensing into new generations of stars and planets. We are built from these elements. The iron in our blood was forged in supernovae that exploded before the solar system formed. The carbon in our cells was synthesized in the cores of red giant stars that lived and died long before the sun was born. The water in the oceans carries hydrogen that dates to the first 3 minutes of cosmic time. In this sense, every question we ask about the universe is also a question about ourselves, about the processes that assembled the atoms of which we are composed, about the stellar and chemical history that made biology possible, about the cosmic context in which life arose and in which, if life is not unique to Earth, it has arisen elsewhere as well. The universe is ancient, vast, and in most of its extent, dark and cold and empty. But it is also the environment in which complexity is possible, in which the laws of physics, operating over billions of years, can produce from simple initial conditions a cosmos rich enough to contain neutron stars, gravitational waves, planetary systems, chemistry, and minds capable of wondering about all of these things. That wondering is itself a feature of the universe worth remarking on. The physics that governs the collapse of a protostellar cloud also governs the propagation of nerve impulses in the brain examining that collapse. The quantum mechanics that determines the energy levels of atoms in distant stellar atmospheres is the same quantum mechanics that determines the chemical bonds in the molecules underlying thought. We live inside the system we are trying to understand, using the system's own products, brains, instruments, mathematics to investigate its properties. This is not a limitation to be lamented. It is an extraordinary fact to be appreciated. The universe has, in the 13.8 billion years since the Big Bang, produced conditions under which some of its contents can reflect on the whole. How far that reflection can reach, how much of the universe is ultimately comprehensible to any mind that could exist within it, is itself an open question. Some aspects of physics may be permanently inaccessible. What lies beyond the cosmological horizon, what conditions prevailed before inflation, what happens inside a black hole singularity. The boundaries of knowledge are not merely practical, but in some cases fundamental, built into the causal structure of space-time itself. A universe with an event horizon is a universe that withholds some of its contents from any given observer by construction, not because the hidden regions do not exist, but because no signal from them can reach us. And yet, within those limits, the accessible universe turns out to be extraordinarily rich. The 2 trillion observable galaxies, the cosmic microwave background, the gravitational wave background, the cosmic ray spectrum, the chemical abundances of the oldest stars, each is a text in a language that physics has spent a century learning to read. We are partway through that reading. What has been decoded is remarkable. What remains undecoded is almost certainly more remarkable still. This is not the conclusion, but a position, a place in the middle of an inquiry that has no foreseeable end. The universe is old, large, and strange. It is stranger than anyone expected when the modern scientific investigation of it began. And the history of that investigation gives every reason to expect that the strangeness is not exhausted, that the next instrument, the next detection, the next careful analysis of existing data will reveal something that overturns a confident assumption or opens a question that had not yet been asked. The universe has been generous with its surprises. There is no sign that it is finished. The nature of time itself, not just the direction of time, but its fundamental character, is one of the questions that cosmology and physics together have illuminated without fully resolving. In everyday experience, time flows in one direction, causes precede effects, the past is fixed, the future is open. But the fundamental laws of physics, both classical mechanics and quantum mechanics, are, for the most part, time symmetric. A film of 2 billiard balls colliding runs equally plausibly forward and backward. The Schrödinger equation governing quantum evolution is time reversible. Only thermodynamics through the second law imposes a preferred direction. And the second law, as we have seen, is itself a statistical statement, a reflection of the enormous number of ways a system can be disordered compared to the small number of ways it can be ordered. The arrow of time is, in this view, not a fundamental feature of the laws of physics, but an emergent consequence of the universe having begun in an unusually low entropy state. Why did the universe begin in a low entropy state? This is ultimately the deepest question raised by the Boltzmann-Brain paradox and by thermodynamics applied to cosmology. The inflationary paradigm offers a partial answer. Inflation stretched any initial inhomogeneities flat and generated a nearly uniform, low-entropy initial state from which subsequent structure formation could proceed. But inflation itself requires initial conditions, a sufficient extent of space in which inflation could begin, and an inflatant field in the right state to drive the exponential expansion.
Whether these initial conditions are themselves natural, whether inflation generically begins given the right fundamental physics, or whether they represent a further fine-tuning problem is actively debated. Roger Penrose has argued, through a quantity he calls the Weyl curvature hypothesis, that the initial low entropy of the universe is encoded in the specific smoothness of space-time at the Big Bang, a condition that appears extremely special when measured against the much larger space of possible initial conditions allowed by general relativity. His proposed resolution, conformal cyclic cosmology, proposes that the universe undergoes infinite cycles of expansion, each ending in a state that, through a conformal rescaling of the metric, becomes the smooth initial condition for the next cycle. In this picture, our Big Bang is the end of a previous aeon, and the universe, in a very precise mathematical sense, is eternal. These speculations are not idle. They make specific observational predictions, patterns in the CMB that should appear if conformal cyclic cosmology is correct. Signatures in the gravitational wave background that distinguish different early universe scenarios, specific correlations in the cosmic ray spectrum that would indicate the influence of physics beyond the standard model. Every theoretical framework, however exotic, eventually makes contact with observation, or it does not survive as a scientific theory. The tension between the grandeur of the ideas and the precision required to test them is itself one of the defining features of modern cosmology. There is also the question of what preceded the Big Bang, if that question has meaning. Within general relativity, the Big Bang singularity is a boundary of space-time, a moment before which the classical description breaks down. The question of what came before is analogous, in some formulations, to asking what lies north of the North Pole. The coordinate breaks down at the boundary, and the question may be grammatically meaningful but physically undefined within the theory. But quantum gravity, the still incomplete union of quantum mechanics and general relativity, may resolve the singularity, replacing it with a smooth quantum transition. In loop quantum cosmology, as noted earlier, the Big Bang becomes a big bounce, a minimum volume, quantum mechanically prevented from collapsing to zero, from which the current expansion phase emerged. In string theory and M theory, the initial singularity may be replaced by a higher dimensional geometric transition, a collision of branes, a topology change in the compactified extra dimensions, or some other process without analog in our four-dimensional experience. Each of these frameworks opens a vista of possibilities for what the universe is and how it came to be as we find it. None has been confirmed. All are, at some level, speculative, constrained by observation and mathematical consistency, but not yet decisively verified. This is the frontier of physics and cosmology, a place where the best tools of human reasoning and instrumentation are brought to bear on questions that press against the limits of what can be known. And at the center of all of it, through every scale, from the quantum fluctuations that seeded the cosmic web to the expansion of the universe itself, runs the constant interplay between matter, energy, space, and time. These four elements, described by the standard model of particle physics and the general theory of relativity, constitute the complete known framework for everything we observe. Yet they are known to be incomplete. General relativity cannot describe the interior of black holes or the universe at the Planck scale. The standard model cannot explain the identity of dark matter, the mechanism behind inflation, or the origin of the matter-antimatter asymmetry that allowed the universe to contain matter at all, rather than annihilating back to pure radiation in the first seconds of time. The next theory, the one that subsumes and extends both of these foundational frameworks, is the goal toward which physics has been striving for a century. That theory may or may not be string theory. It may or may not involve extra dimensions, supersymmetric partners, or modifications to the geometry of space-time on short scales.
It may involve entirely new concepts for which we do not yet have names, just as the concepts of space-time curvature and quantum superposition required entirely new mathematics to formulate. The history of physics strongly suggests that the next deep theoretical framework will be more general, more unified, and stranger than anything currently proposed.
It will likely require the same kind of conceptual revolution that general relativity and quantum mechanics each demanded, a willingness to abandon assumptions so deeply embedded in our thinking that we did not even recognize them as assumptions. The universe, in this sense, is not merely an object of study. It is a partner in the investigation, revealing, through the behavior of its contents at every scale, the properties of the laws that govern it. Black holes that violate information conservation push us toward quantum gravity. The accelerating expansion reveals dark energy and demands an explanation. The Hubble tension hints that our current model may be missing something. Early massive galaxies strain our models of galaxy formation. Each anomaly, each tension, each surprise is the universe's way of pointing at the places where our understanding needs to grow. We followed those pointers. We built instruments designed to look more precisely at the places where our models strain. We construct mathematical frameworks that can accommodate the new observations, and the universe generously continues to be more complicated than our previous best understanding. This has been true at every stage of the scientific investigation of the cosmos. It was true when Galileo turned his telescope on Jupiter and found 4 moons that disproved the geocentric model. It was true when Hubble looked at the Andromeda Nebula and determined it was a separate galaxy, millions of light years away, transforming the known universe from a single Milky Way to a cosmos of billions of comparable structures. It was true when Penzias and Wilson detected the cosmic microwave background, an accidental discovery that confirmed the Big Bang and revolutionized cosmology overnight. It was true when the supernova survey teams discovered the accelerating expansion in 1998 and overturned the expectation that gravity was slowing the universe down. And it will be true again, the next overturning is coming. As certainly as all the previous ones, driven by instruments not yet built examining phenomena not yet characterized, what remains to be discovered in the universe is, by any reasonable estimate, vastly larger than what has already been found. We have characterized the contents and history of the observable universe to remarkable precision. But the observable universe is a sphere 93 billion light-years across, in a cosmos that may be infinite in extent. The laws of physics we have discovered apply throughout the observable universe, but we do not know whether they apply universally, whether the physical constants that govern our experience are the same in regions we cannot see. We do not know whether the universe is the only universe, or one of a vast or infinite collection. We do not know whether the dark matter and dark energy that make up 95% of the universe's energy content have properties that will someday illuminate entirely new sectors of physics. We do not know whether life is rare or common, whether intelligence is a typical or atypical outcome of biological evolution, whether we are among the first civilizations in the universe or among the last. These are not small questions. They are the largest questions that can be asked. And they are all in principle accessible to observation, to experiment, to the patient accumulation of knowledge across generations of scientists using tools that each generation could not have anticipated. The universe is old, and it has been producing surprises for all 13.8 billion years of its existence. It will continue to do so for far longer than that, for the trillions of years of the stelliferous era still to come, for the slow cooling of the degenerate era, for the long evaporation of the black hole era, and perhaps in some form or another, for whatever comes after. It is not finished. We are not finished. The investigation continues.